In this lecture, we are going to explore a new topic. It's an amazing topic, Faraday's law. This discovery changed our whole world. The generators were created and the power plants were established. It contributed greatly to the technological revolution as well as the development of economics. But it's also a difficult topic since it's a law beyond our intuition. So I will spend more time discussing this topic in details. Please recall the experiment did by Ørsted. He found that the magnetic needle deflected near a wire carrying a current. This phenomena told us that the electric field could produce the steady magnetic field. The connection between electricity with magnetism was discovered. After that, this guy, Faraday, had a wonderful idea. He thought, since the electric field could produce the steady magnetic field, maybe the steady magnetic field could also create the electric field. With that wonderful idea, he did a lot of experiments, but he failed. He could not see any current created by the magnetic field. He never gave up and he persisted. One day, an amazing phenomenon was observed finally. He noticed that at the instant when he opened or closed the switch, the current was produced. Let me show you the setup of his experiment. Here is the iron ring. Some loops are around the iron. We call it the circuit 1. There is a battery in the circuit 1. Another part we call the circuit 2. We notice that the circuit 2 is not connected to the circuit 1, and we don't have the battery in the circuit 2. We connected an ammeter in the circuit 2. When we close the switch, a current is going through the wire and a steady magnetic field is established. And the magnetic flux also penetrates through the circuit 2, but we could not observe the current in the circuit 2. That means the existence of the magnetic field cannot bring us the current. However, at the instant the switch is closed or opened, the reading of the ammeter was changed. That means the current was created in the circuit 2. It's amazing. No battery in the circuit 2, but the current there. So, what produced the electric current? What do you think of this observation? We know at the instant we close or open the switch, the magnetic field is changing. Thus, it's not the magnetic field that produces the electric current, but the changing magnetic field creates a current in the loop. Change is the requirement. If the magnetic field remained the same, no current. We call this amazing phenomena electromagnetic induction. We call this current in the circuit 2 an induced current, which is produced by the EMF as if a battery is present in the loop. But this EMF is called induced EMF, which is created by a changing magnetic field. This is a conclusion made by Faraday based on these experimental observations. The key point is an induced EMF. Imagine the conducting wire is replaced by a plastic loop. Do we have the current? No. Why? Because the plastics is insulating and no free electrons. But an induced EMF is still there. Experimentally, there are some ways to create an induced EMF. As shown in these figures, we can change the magnitude of B, we can change the area enclosed by the loop, and we can also change the orientation of the loop with respect to the field. Induced EMF will be created by all these methods. So, what conclusion can we make based on these experimental results? We mentioned the magnitude of B, the area of the loop, and the angle between B and the plane of the loop. So, it's the changing magnetic flux through the loop that produces the induced EMF. Now, we arrive at Faraday's law. Here is a statement. The EMF induced in the circuit is directly proportional to the time rate of change of the magnetic flux through the circuit. This statement can be expressed mathematically as Faraday's law of induction. Epsilon equals negative of derivative of phi b with respect to time. What's phi b? Phi b is the magnetic flux. Based on the definition of the magnetic flux, phi b equals the integral of b dot dA over the surface. If we have n loops with the same area, we can imagine the flux will penetrate through the surface n times, so the induced EMF is n times larger as expressed by this one. We have noticed that there is a negative sign in this equation. What is the physical meaning? Lenz's law gives us the interpretation for that. Let's look at the example as shown in the figure. Here is a loop. We have a magnet. The magnetic field lines are shown here. When the magnet is moving toward the loop, the upward flux through the loop is increasing. In this case, the induced current in the loop is in this direction as shown in the figure. Based on the right-hand rule, the magnetic field produced by the induced current should be directed downward. This is just opposite to the direction of the original magnetic flux, opposing the increase of the original flux. If the magnet is moving away from the magnet and the upward flux through the loop is decreasing, then the direction of the induced current is reversed. Therefore, the magnetic field created by the induced current is always opposing the change of the original field. This is Lenz's law. The induced current is in the direction which produces a magnetic field that opposes the change in magnetic flux. Lenz's law explains the physical significance of the negative sign in the mathematical expression of Faraday's law. If the original magnetic flux is increasing, the field produced by the induced current will oppose this increase, vice versa. That means the induced current tends to keep the original magnetic flux from changing. Actually, Lenz's law is the law of inertia in electromagnetism. In the next lecture, we'll discuss the induced EMF in more details.